Okay, in this lecture we will talk about microvalves. Microvalves are another important component in microfluidic devices, which is used to manipulate flow rate inside microfluidic devices. Okay. And the microvalves can be categorized as into two different types. One is the passive microvalve, which is does not require any external energy. Typically it will have a spring, and when the inlet pressure exceeds a certain value, then the spring will deflect and the flow will come in from an external source into the valve chamber. And in active valve there will be an actuator which will be controlling the force exerted onto the chamber, the valve chamber, and accordingly the valve port can open. Okay. So, microvalve is a component in microfluidic device used for manipulation of flow rate. Okay. So, the microvalves can be categorized into passive microvalve, which does not require any external energy. So, one example would be the check valve that we have discussed when we were talking about micropump, and the second one is active microvalve. Okay. So, in the active microvalve we would have an actuator that would control the position of the valve seat to manipulate flow. And the flow can be manipulated in two ways. One is the analog mode, and the second one is the digital mode. Okay. So, in the analog mode, as you can see here, in the analog mode the valve actuator will control the gap between the valve seat and the opening to control the flow rate. So, as the gap varies, as the gap increases, the flow rate will increase, and as the gap reduces, the flow rate will decrease. So, the analog mode, in the analog mode the valve actuator varies gap between the valve seat and the opening to control flow rate. Okay. And the second one is the digital mode, and as you can see here, in the digital mode the valve is either open or closed. As you can see here, this is the close cycle of the valve, and then at some arbitrary time t0 the valve start to open, and so here initially the valve is open, and then at some arbitrary time t0 dash the valve starts to close. Okay. So, in the digital mode the valve is fully open or fully closed. Okay. So, the valve is fully open or closed. And the valve can also open in the digital valve can also operate in what is called pulse width modulation mode, in which case the opening time of the valve will control the flow rate. Okay. So, the digital valve can operate in pulse width modulation mode, okay, pulse width modulation mode. So, in that case the flow rate controlled by the opening time. Okay. Right. Now, let us talk about different types of microvalves that exist. So, these different types of microvalve are categorized based on the actuator, the actuating principle that drives these microvalves. Okay. So, let us talk about different types of microvalve. Okay. So, one is pneumatic, which uses the principle of external pressure. Then you have thermopneumatic, which uses external heat to generate pressure inside. Then we have thermomechanical, which uses external thermal energy to generate mechanical energy. Then piezoelectric, okay. Then we have electrostatic, then we have electromagnetic, and we have electrochemical. Okay. So, we will be discussing each of these types of microvalves. Okay. So, let us first look at the designs of different types of microvalves. So, this is a pneumatic microvalve where, so this is the inlet supplied connected to the external source, okay, fluid source, and this is the valve actuator. Okay. This is the disc which is being actuated by external supply. When this line is connected to the external supply and the external pressure, the P supply pressure is greater than the spring constant plus the inlet pressure, then the valve would be in the closed state. Okay. And when this external pressure is taken off, the membrane goes back to its original position because of the spring force. So, the valve is open. Okay. In similar way, here in this is the pneumatic, okay, and this is thermopneumatic. Here we have an array of heaters, and there is a fluid present here inside, and when the heat pulse is applied to the heaters, there is the bubbles are formed, and these bubbles expand. When they expand, they will actuate this membrane. Okay. So, that is how the valve will be controlled. So, this is actually a thermomechanical valve, okay, and here the heater is present on top of the membrane. As the thermal energy is applied, because of the thermal expansion, the valve will be actuated. And this is a piezoelectric actuator, okay, and here by applying an external electric field, a strain could be developed in the piezo material, which is used to actuate the valve. And this is a piezo disc, and here we are talking about a piezo stack. Okay, several of these discs placed on top of each other. So, it is a piezo stack, and this is electrostatic. So, that basically relies on the attraction force between two oppositely charged electrodes for actuation of the membrane. This is electromagnetic. Okay. And this one is the electrochemical. So, in electromagnetic, the magnetic force is actually trying to actuate the membrane, and here in electrochemical, electrolysis at the electrode generate these gas bubbles, which tend to expand, thus expand and contract when the thermal pulse is taken away. So, that is how the membrane is actuated. Okay. So, now let us define some parameters that specify different microvalves. Okay. So, let us look at the microvalve specifications. So, the first thing is the leakage ratio. So, leakage ratio is the flow rate through the valve in a closed state to that in the open state. Okay. So, the leakage ratio, which is specified as L valve, is defined as the flow rate through the valve in the closed state divided by the flow rate in the open state. Okay. And if there is no leakage in the closed state, the leakage ratio is going to be 0. Okay. So, this is the flow rate in closed state, and this is flow rate in open state. Okay. The second parameter that we are defining is the valve capacity. Valve capacity as the maximum flow rate that the valve can handle. Okay. So, this is the maximum flow rate valve can handle. So, is specified by C valve, which is given as Q max. So, it is the maximum flow rate divided by delta P max divided by rho Z L, square root of that. Okay. So, that is how we specify the valve capacity. Now, here Q max and P max are flow rate and pressure drop at fully open position, and L is the characteristic length of the valve. Okay. The characteristic length of the valve. The third parameter that we specify is the power consumption. So, it is the total power the valve will consume in active state, and so this will be the total power consumed in active state, and the power would depend on the actuating principle. And this is going to be high for thermopneumatic. Okay. The next parameter that we specify is the closing force. So, closing force it depend on the pressure generated by the actuator and the next one is the temperature range, which will depend on the valve material and the actuation concept. Then the response time, how quickly the valve is going to respond, that would depend on the actuator type. And electrostatic valves have got very less response time. Okay. So, electrostatic valve short response time. Okay. Then reliability, so reliability will depend on the actuator and the operating conditions. And operation failure, so one major reason why valves should fail is when there is particle inclusion in the flow. Okay. So, when the particles will be included in the flow, what happens is these particles will tend to stick between the valve seat and the valve structure, and that is how the leakage or the valves will fail. Okay. So, one way to handle that is to use filter. Okay. So, operation failure, one major reason is because of particulate contamination, and so it is important to use filters. Okay. Now, let us look at a few parameters that we would be using to design microvalves. One important parameter is the energy that is supplied by the actuator. Okay. How we can calculate the different energies for different types of microvalves. Okay. So, let us look at the design considerations. So, first important consideration is the work produced, which basically characterizes the performance. So, the work produced would be the actuator force into the maximum displacement. Okay. This is the actuator force, this is the maximum displacement. Okay. Now, we define energy density. So, in micro scale, in addition to talking about how much work is produced, the actual physical size of the device is also important. So, it is the energy density which will rate a particular microvalve. Okay. So, this rates the microvalve. and this is because the size is crucial for miniaturization. So, we can define energy density as the work produced per unit volume. Okay. So, that is FA into SA divided by V. So, where V is the volume of the actuator. Okay. So, now let us find the energy of thermomechanical actuators The energy is given by the expression half into stress into strain. Half into stress into strain. Okay. So, the strain in case of thermomechanical is going to be the thermal expansion coefficient into temperature difference. Similarly, the stress is going to be Young's modulus times the strain. So, gamma into delta T. So, you can find out the energy which is going to be half into E gamma delta T into gamma delta T, and which is going to be half E gamma delta T square. Okay. And this is because the stress is proportional to strain and the energy is area under the stress strain curve. Okay. So, let us say this is stress and this is strain, then we would have the energy within the area. Okay. Next, we can find the energy of a piezo actuator. So, the energy of a piezo actuator is half into the electric field divided by the piezoelectric coefficient into Young's modulus square. Okay. So, this is the electric field, this is Young's modulus and this is the piezoelectric coefficient. Okay. Similarly, you can find the energy for an electrostatic actuator. You can find energy for an electrostatic actuator. So, for the electrostatic actuator, the energy is given by half into epsilon into the square of the electric field. Okay. So, this is the dielectric constant, this is the electric field. So, when you are talking about electrostatic actuator, we are talking about the energy stored between the two parallel plates of the electrostatic actuators, and here in this case, so the expression is given by half into epsilon into electric field square. So, epsilon is the dielectric constant of the medium between the two parallel plates, and this is the electric field. Okay. Next we talk about for a magnetic actuator. For a magnetic actuator, energy will be given by half into B square over mu, where B would be the magnetic flux density and mu would be the permeability of the medium. Okay. So, with that design conditions, let us look at the response time and the pressure characteristics of different types of microvalves. So, here we see the pressure, the response time and the energy density of different types of microvalves. You can see the pressure is given in kilopascal, and you can see for low pressure range somewhere between 1 to 100 kilopascal we would have electromagnetic, piezoelectric, electrostatic and electrochemical. In the medium range between 10 to the power 200 to 10 to the 4 kilopascal we would have pneumatic, thermopneumatic, SEP memory alloy and thermomechanical. Piezoelectric type microvalves can offer the highest pressure. Okay. So, anything higher than 10 to the power 4 kilopascal can be obtained using piezoelectric type micropump, especially stack type piezoelectric, where we have multiple discs mounted on top of each other. Okay. If you look at the response time, as we discussed before, electrostatic microvalves have got very good, very low response time, and the piezoelectric and electromagnetic microvalves have response time between 10 to the power -4 to 10 to the power -3, and then the response time of thermopneumatic and thermomechanical is between 10 to the power -3 to 1 second. Okay. And the microvalves like pneumatic, SEP memory alloy and electrochemical, their response time is very poor. Okay. So, they have response time higher than 1 second. So, you can see that there is a trade off between the pressure and the response time. And if you look at energy density, the electrostatic microvalves have very low energy density. So, they have energy density between 10 to the power 2 to 10 to the power 3, followed by a magnetic which is less than bimetallic, and the thermopneumatic microvalves have energy density of the order of 10 to the power 6 joule per meter cube, and the piezoelectric and SEP memory alloy have got very high energy density of the order of 10 to the power 7 joule per meter cube. Okay. Now, with that let us look at the pneumatic micropump. So, we look at what pneumatic microvalve is. So, with that let us look at pneumatic microvalve. So, we will first try to understand what a pneumatic microvalve is, understand the operational principle and take on a design problem. Okay. So, let us talk about pneumatic microvalve. As you can see here, this is the valve membrane. Okay. So, this is the valve membrane, as you can see here, this one is the valve membrane. This is the inlet to the fluidic source and this is the outlet, and this one is the valve seat. Okay. So, this is the the top side of the membrane is connected to a pressure chamber. Okay. Now, when this pressure is more than a critical value, then the membrane will deform and the valve will be closed. Okay. And when this supply pressure is taken off, then the spring constant, because of the spring constant of the valve membrane, the valve is going to open up. Okay. So, the actuation of the valve is going to take place by controlling the pressure inside the chamber, and which can happen by controlling the external pressure. Okay. So, what are the characteristic of pneumatic microvalve? The pneumatic microvalve have simple actuation concept. Okay. So, the actuation concept is very simple, but since we are talking about connecting with external pressure source, and these external pressure source are larger in size, and we would require interconnection mechanism to connect fluidic supply with the microvalve. The size of the microvalve is a concern. Okay. So, because of that, these microvalves are not suitable for miniaturization. Okay. Or they are not suitable for compact application, and they have widest temperature range. They have wide temperature range. Okay, this is because when you apply a pressure, irrespective of the temperature, the membrane is going to deform. Okay. So, these pneumatic microvalves will have wide temperature range. Okay. So, this is because the membrane deflection occurs irrespective of temperature. Okay. And the pneumatic microvalve should be optimized for. So, the optimization criteria we should try for low actuating pressure, that should be one design goal, and we should try for low leakage, and we should also try for low spring constant of the membrane. Okay. Now, since we are controlling the microvalve or the membrane actuation using an external supply, the response time of the microvalve would depend on how the control is happening for the external supply. Okay. So, the response time would depend on the external switching device. Okay. And due to large system size, the response time is typically large. Okay. So, the response time is of the order of hundreds of milliseconds, hundreds of millisecond to several seconds. Okay. So, the response time of pneumatic microvalve is poor. So, with that, let us look at a design problem. So, this is the problem we have. We have a pneumatic microvalve that has circular silicon membrane as the valve seat. The membrane is 20 micron thick and has a diameter of 4 millimeter. Okay. It is 20 micron thick and it has dia of 4 millimeter. The valve is normally open with a gap of 20 micron between the membrane and the valve inlet, and we want to determine the pressure that is required for closing the valve at an inlet pressure of 1 bar. Okay. And the opening diameter is given, which is 200 micron. Okay. So, typically we have a configuration something like this. So, we have an inlet, okay. So, this is the inlet and this membrane is going to deform to actuate the valve, okay. And this is about 20 micron and this is 4000 micron diameter, okay. And we have the supply pressure is 1 bar and this gap is 200 micron, okay. So, now if we assume a distributed load on the membrane, so let us say the external pressure applies an uniformly distributed load on the membrane. So, we make an assumption which is uniformly distributed load on the membrane, and we say that the Poisson's ratio nu is 0.25 and Young's modulus is 170 gigapascals, thus for silicon, okay. So, these are for silicon. Now, if you assume that the deflection is small, for small deflection, we have an expression for the spring constant of the membrane, okay. So, for small deflection the spring constant can be written as 16 pi E t cube over 3 t square into 1 minus mu square, okay. So, we can plug in the values. 16 into pi is 170 into 10 to the power 9 and thickness is 20 micron. So, divided by 3 into 2 into, sorry, this is r square, this is the radius is 4 millimeter. So, the radius sorry the diameter is 4 millimeter. So, the radius is 2 millimeter into 1 minus 0.25 square. So, we will get the spring constant as 6.08 into 10 to the power 3 Newton per meter, okay. Now, if the valve is closed, then the total pressure that is exerted on the membrane because of the external pressure will be equal to the pressure that is at which the fluid is trying to come in plus the spring constant, spring force exerted by the membrane, okay. So, if microvalve is closed at the actuation pressure, then we can write down the force balance. So, which will be the actuation pressure into the area of the membrane is going to be P in into A in plus the spring force. Okay. So, the pressure inlet is here. So, the force it will try to exert will be on this area. So, that is A in, and area of the membrane is the entire area, top area here. Okay. So, you can write the P actuation would be P in plus K into delta x over area of the membrane, which is given by 10 to the power 5 plus 6.08 into 10 to the power 3 into 20 into 10 to the minus 6 divided by pi into 2 into 10 to the minus 3 square. Okay. So, that would be about 109.67 kilopascal. Okay. So, we need this amount of pressure to close the microvalve. Okay. So, with that let us move on and talk about thermopneumatic microvalve. So, let us talk about thermopneumatic microvalve. So, the thermopneumatic microvalve basically rely on the change in the volume that happens inside a chamber because of some kind of phase change. Okay. So, it could be because of heating the fluid, that the fluid will convert into the liquid will convert into gas, or a solid will convert into liquid, that the volume of the chamber would increase. So, that would actuate the membrane for actuating the valve. So, as you can see here, we have a pressure chamber. Okay. And so, there is a liquid present inside, and we have an array of heater that you can see here. So, when heat energy is added to the fluid, the liquid starts to, if the heat is enough, then the liquid starts to get into the gas phase. Okay. So, there will be nucleation and expansion of the bubble, and because of the expansion, this membrane here is going to be actuated, and as this membrane, as the volume inside will grow, the membrane will get in touch with the valve seats. Okay. So, that is how the valve is going to be closed. Okay. And when the heat pulse is taken away, again the valve can open. So, that is how the valve is going to be actuated. So, the principle is shown here. Let us say this is the inlet and this is the outlet. So, typically we have a liquid present inside the chamber here, and as heat is supplied, initially let us say this is, there is no phase change. Okay. So, this material is still in the liquid phase. So, now here the volume expansion would be because of the heating, okay, because of the thermal expansion coefficient of the liquid. Okay. Now, if the temperature is enough, then the liquid there will be the nucleation of the bubble will start to occur, and as the temperature as the heat is continuously supplied, these bubbles will grow. So, this membrane is trying to expand. Okay. And at some point the gas will be completely filled inside the chamber and the membrane will seal the inlet as well as the outlet. So, that is when the valve is completely closed. Okay. So, what are the characteristics? So, we are basically relying on change in the volume of a sealed liquid or solid under thermal loading. Okay. And in this case the mechanical work is greater than the energy stored in electrostatic or electromagnetic field. Okay. Now, let us say the volume is V and mass is m, then the specific volume can be V can be written as V over m, which is 1 over rho. Okay. And as you can see, as the chamber is sealed, the mass is not going to change. So, the specific volume is going to be directly proportional to the volume of the chamber. Okay. So, as chamber is sealed, m is constant. So, the specific volume is going to be proportional to the chamber volume. Okay. So, now let us look at 3 different processes that we see here. So, let us say the process 1. So, here there is no vapor phase. So, it is still liquid and there is a change in the temperature. So, in that case the thermal expansion coefficient will come into play. So, in this case the change in the volume delta V is going to be V0, which is the initial volume, into the gamma f, which is the thermal expansion coefficient, into T2 minus T1. Okay. And so, if in this case the valve is going to be closed, the specific volume is going to be constant. So, the specific volume is constant. Okay. And the pressure will be determined from the properties of the compressed liquid. Okay. So, pressure is determined from properties of compressed liquid. Okay. And let us say the next process, the process 2, let us say, so where, so it is a mixture of liquid and vapor, mixture of liquid plus vapor. So, there is a phase change. Okay. And so, as there is a phase change, the temperature as well as pressure, temperature and pressure both increase due to heat transfer. Okay. And so, in that case we can define something called a mass fraction of the vapor, which will be equal to V minus Vf over Vg minus Vf. Okay. So, this is the mass fraction of vapor and this is specific volume of liquid and this is specific volume of vapor. Okay. Now, let us look at the third case. So, here we have the complete vapor and it could be superheated. Okay. So, in the third case, let us say we call it process. So, in this case the liquid vapor mixture is converted to superheated vapor. Okay. So, there the pressure could be determined. So, P 0 into exponential minus L 0 over R T. Okay. And where this is the universal gas constant and this is temperature, and L 0 is the molar latent heat of evaporation of the liquid. Okay. So, let us stop here and we will continue our discussion with microvalve.